name is Luís Cordeiro, and I'm going to present the Switch2Steel workshop today. And this workshop is organized by a partnership between OneSource, an SME in Portugal, University of Coimbra, Civil Construction Department, CMM Association, and INSIS Research Institute. These activities are co-financed by Centre 2020, Portugal 2020, and the European Commission. So today the agenda will start with a couple of presentations about the project that we have been developing in the last years, and we will start with an introduction to the fire safety in the industrial buildings by Aldina Santiago, then a presentation about the platform that was developed throughout the project by myself. We will go then to a presentation about the background in the algorithms and the design and optimization of buildings. We will have a short break afterwards, and then the presentation about the optimization on fire protection. Then finally, we will have a presentation by Nicola Tondini about the behavior of steel pipe racks subjected to localized fires. And at the end, we will have a closing session, Q&A, and we will be able to answer questions that you may have. So to start the workshop for today, we will start with our presentation by Aldina Santiago. Aldina Santiago is Associate Professor at the University of Coimbra, with a PhD in structures and mechanisms of materials. The research activity from Aldina is mainly on behavior of structures subjected to accidental actions like fire, impacts and explosions, and robustness of structures.
Okay, good morning to all of you. My presentation is about the fire safety design for industrial buildings and infrastructures. I organized this presentation in 4 topics. I will start first with an overview of the problem, and after I will go more in detail about the legislation and about the fire safety design in this type of buildings. Okay, the 2 main questions that we need to answer at the beginning is what it means industrial buildings and infrastructures in this scope. And after we have a second question, why it's so important to make and to be aware for the fire safety design for this kind of buildings. So I will start first with, I will try first to answer the first question. So, when we are speaking about industrial buildings and infrastructures, but first in the industrial buildings, we are speaking about warehouses and distribution, and I have some topics about what it means, these warehouses and distribution. It is used for storage and transportation of goods, and normally we have a single-story building with a large dimension, normally with areas higher than 500 square meters and with a height higher than 15 meters. But we are also talking about manufacturing facilities with heavy equipment, with normal, and this is very important for this subject, fire safety design, normal, this kind of building with 3-phase electrical power, with a high capacity of ventilation and a high system of exhaustions. And also in general, these buildings also have pressurized air, water lines with floor drains and storage tanks. But we are also talking about refrigeration and cold storage, normally used for food products with small or large rooms for cooling and freezing. And we are also talking about buildings for telecom and data hosting centers, again, large facilities with extensive computer services and associated equipment, with normally redundant power supply, with heavy equipment, and if you can see here, normally with a strong floor to support this high equipment. And about infrastructures, we may say the tunnels, the terminals, large compartments, at least in one direction, in this case, with a high ventilation. So we have here some examples, at least 6 examples of the scope of the buildings that is in the scope of this presentation. So this is, we try to answer to the first question. And now about the second question. Why is so important to take into account the fire safety design for this kind of buildings? Probably because I'm more aware about this issue in the last times, but if you find in the news, at least in Portugal, but I think it is around the world, you saw that we have a lot of news about fires in this kind of buildings. For example, in the last weeks, we saw a fire in the cod processing factory here in Coimbra. We had another fire in a recycling factory in a marsh in the north of Portugal. And again, in the north of Portugal, a fire in a refrigeration factory in Vila de Conde. So, and I also tried to find official numbers, and from 2021, the last official numbers that we have a number of 654 industrial fires in Portugal. What it means, more or less, or near 2 fires per day in industrial buildings. So this is too large. The number of fires in industrial buildings is too large, and this is the reason why we started this project, and this is the reason why we now, at the end of the project, we have this seminar. So, and what are the main causes of the fires? The hot works, mainly in manufacturing factories. We have also the combustible dust. This kind of fire with this combustible dust are fires that the temperature increase very, very fast, and fires where it is very difficult to stop and to extinguish. But we have also in warehouses, we have also as a cause of the fires, the flammable liquids and gases. We have also the bad maintenance and sometimes human errors in equipment and machinery. And the most critical causes of the fire in this kind of buildings are the electrical hazards. We know that normally 20% or more than 20-25% of the fires in industrial buildings are due to electrical hazards. So, and in terms of impact, first we have the human life. Normally these buildings are factories with a lot of works, and the main attention, the first attention is for the human lives, the safety of the human life. But we have also the properties. We have in these buildings, we have equipment, very expensive equipment, machinery, raw material, all of them normally very expensive, where the damage and sometimes the destruction of this equipment will contribute for large financial losses. But we have also to take into account the environmental. In these buildings, sometimes we have other materials, we have chemics, and due to the fire, they could contribute to the toxic gases, they could contribute to the air pollution, they could contribute also to the contamination of the waters. And of course, at the end, we have the loss and the interruption in the economy and in the business of these factories. So now I will pass to the second point, and the second point is related to the legislation. I will start first with the presentation, overview, a short presentation about the Portuguese legislation for this kind of buildings, and after I will make a comparison with the European legislation. So starting with the Portuguese legislation, we have two documents. Decree law number 123, the last version is from 2019, and we have a technical regulation 1532, and the last one is not from 2008, but the main contents is in the version of 2008. So in the first document, we have the organization of the different types of buildings and enclosures. We have defined, at this moment, we have defined 12 standard use for the different buildings. And for each one, they are organized in 4 risk categories. Okay, after I will show how to calculate this risk category. In the second document provides the technical regulation for the fire safety design in terms of fire behavior, insulation, fire protection. So first we make a characterization, and after we will do the fire design. So starting with the first document, as I said before, we have 12 standard uses. All of them are here. And for this specific case, for the industrial building, we have in the standard use number 12, industrial buildings, workshop, and warehouse. And after, as I said, we need to calculate the risk category. We have 4 risk categories from the first to the 4th. The first one is a reduced risk, and the 4th category is a very high risk. How to calculate this risk category? There are a table that is defined in this decree law that it allows to calculate this risk category based on the number of floors below the ground floor, and also based on the modified fire load. This modified fire load, it is calculated, would be calculated based on a deterministic approach or based on a probabilistic approach. But in both cases, this modified fire load, it depends of the materials, it depends of all of the contents of the compartment. In this case, the industrial compartment. Okay, so after that, it is possible to define what is the risk category for our building. And after, we have this table in the second document, in the technical regulation, where it is possible, based on the utilization type, in this case 12, and after to calculate the category of risk, it is possible to calculate the fire resistant time. And the fire resistant time, it could be for the first risk, the first category of risk, it could be 60 minutes or 180 minutes. The minimum in the Portuguese legislation for this kind of buildings is a fire resistance time of 60 minutes. What it means that I need to design all the structural elements to resist during 60 minutes. Okay, and now the comparison with the English legislation and also to the French legislation. It is easy to see that the way how to calculate this fire resistant time, it is different. As I shown before, in the Portuguese one, it is based on the modified fire loading. But for the English one, it is based on the height of the building, and after it is considered if I put sprinklers or not. In the Portuguese legislation, it is also imposed to put sprinklers, but they are not taking account in the design, the calculation of the modified fire load. I need to put sprinklers in the building, but after I disregard them in the design. And in the French legislation, the fire resistant time is calculated based on the number of floors. So again, what another difference? If you see, the minimum resistance time in the English legislation could be 30 minutes, in the French legislation could be 15 minutes, and in the Portuguese legislation is 60 minutes. What it means that our legislation is much more severe than the similars in other countries of Europe. And now I go to the third topic, the principles of the fire safety design. First, starting with the fire safety of the industrial building, the main concepts. First, the fire prevention, okay? A good maintenance of the equipment, for example, but also the fire detection and the alarm system, the detection of the smoke, the detection of the flames, but also the need but this is imposed on the design, the emergency planning and evacuation. All of the occupants of the building should know and should understand the fire evacuation plan. And after the existence of fire suppression systems, for example, sprinklers, the good storage of the other materials, the continuous training and education of the workers, and at the end, and probably more directed to our seminar, the design of the structure according to the standards and taking account the necessary fire protection for the structural elements. And now looking to this last topic, the structural fire protection, we could take two approaches for the design, and I divided these two approaches taking account the typology of the buildings. If we have a small compartment, it is possible to assume that we have a uniform temperature in all the compartments. So it is possible to assume the same temperature in each point of the compartment, and this temperature could be calculated based on the nominal curves that we have in the standards. However, if you have large compartments with non-uniform temperature, with large ventilation, it is very difficult to have a uniform temperatures. So the nominal curves that I have in the small compartments are not possible to use in this kind of compartments. And we have for the industrial compartments, we have this situation. So the linear rules, the linear equations that we have in the standards is not possible to apply for this kind of buildings. In this kind of buildings, we should make the design based on the real performance of the building and taking account all the conditions of the building. And according to the Eurocodes, it is possible to do first, when we have, as I said before, a well-defined compartment, it is possible to do a prescriptive approach design. And in this prescriptive approach design, we made the design based on nominal curves. We have, for example, the well-known ISO 834. And after that, we made the analysis of the structure. That could be the analysis of elements, substructure, or the entire structure. And after that, we made the design of the elements or the substructure or the structure. And the design for the elements, for example, it could be based on tables, tabulated value, not for the steel structures, but for example, for the concrete structures. It is possible to do a design based on tabulated values. And after, it is possible to do the design based on simplified equation or more sophisticated equations. When is needed to use a design performance-based design, so we have for sure, we have more complex calculations. Yes, it's for sure, but we have a more precise response and to have the correct response in each point of the compartment. It is possible to have the variation of the temperature in each point of the compartment. It is possible to know the transport of smoke. It is possible to know the transport of heat. We have all the details in the compartments. So in this case, we have more accurate design, and sometimes it could be a more economic design too. So, and if you see in this layout from the Eurocode, when we use a performance-based design, the design of elements of substructures are not allowed using tabulated values. In this case, we could use for the elements, we could use simplified models, but after, for the substructure and for the entire structure, we need to use advanced models and normally finite element models. Okay, and now I go to the fourth point, structural protection and fire-resistant materials. So according to the legislation that I shown before, we should divide the measures, the fire protection measure in two types. Active measures, and I already mentioned some of them, like for example, the sprinklers, the smoke detector, the flame detector, and the passive fire protection measures. In this case, because I'm looking now for the construction materials, I'm focused on the passive fire protection measures. And in the passive fire protection measures, I have to take into account two different systems. First, the structural system, and for the structural system, I need to ensure the stability and the integrity of the building in case of the fire. But when we have also non-structural systems, we need also to take into account the limit of the propagation and the fire development. And now to account these two topics, there are tests, there are standard tests, and the first one is a fire reaction test. What it means, the fire reaction tests are tests that evaluate how the material contributes to the development of the fire. Or better, how do they contribute to the beginning, to the development, and to the propagation of the fire, okay? And based on in these steps, it is possible to classify the materials in different classes. Class F, what it means that these materials has no performance under fire. Okay, and class A, it means that this material has a good performance under fire. It is non-combustible material. And we could say that in class A, we have the concrete, we have the glass, we have the stones, we have the steel. Okay, these materials don't contribute to the ignition and to the development of the fire. And now the second topic is about the other tests, the fire-resistant tests. In this case, I'm not evaluating the behavior of the material, their contribution to the fire, but I'm evaluating the structural system in terms of their resistance in fire, load-bearing capacity, insulation, and integrity. Okay? I put load-bearing capacity, insulation, and integrity. We have here in the lab, we have furnaces where it is possible to evaluate this fire-resistant capacity of horizontal and vertical elements, and it is possible to apply different curves, different thermal load in these elements. The standard curves, but also parametric curves. Okay, after that, after to show the reaction and the resistance of the materials, I go directly to the standards. And the design of this kind of elements is based and is made according to the Eurocodes. We have first the Eurocode 1, and the Eurocode 1 is the Eurocode to define the loads. And in this case, because I'm looking for the fire, for the thermal loadings, I should look to the part 1.2. Okay, Eurocode 1 part 1.2 is related to the thermal loadings. And after I need to go to the design. And the design, there are several Eurocodes. The part related to the fire is always the part 1.2. Eurocode 2 related to concrete, Eurocode 3 related to steel, Eurocode 4 related to composite structures. Okay, normally this kind of buildings, industrial buildings, are constructed by steel elements. I put here some of the advantages of these steel elements, but I think all of you know, but I will focus in, I think that is one of the most important advantages for this kind of buildings. Design flexibility, allowing future expansion and facility to a fast construction. I think, of course, all of them are advantage of the steel, but I think the third one is the advantage that is directly to this kind of buildings, the industrial buildings. So I shown before fire reaction and fire resistance, how to behave the steel according these two types of tests. First, fire reaction. As I said before, steel is a non-combustible material, is in class A, okay, very good. But the problem is about the fire resistance. And when I look to the fire resistance of steel, I know that the strength of steel degrades very fast with the increase of the temperature. I also know that the thermal conductivity of steel is very high, around 15. For concrete, I think it's 1, 2, more or less. And we know that the steel profile have a slender, very, very slender when compared, for example, for other cross sections. So the temperature increase very fast in the cross section of the steel. I put here to show, I said before, that the strength of steel degrades very fast. I put here the curves of the degradation of the properties of steel with the temperature from 20 degrees to 800 degrees. I have some notes. The steel softened progressively from 100 to 200 degrees up. The steel began to lose strength above 400 degrees. Only 23% of ambient temperature strength remains at 700 degrees. At 800 degrees, strength reduced to 11%, and at 900 degrees to 6%. And normally, the temperature in a fire in this kind of building is around 1,000, 1,200, or less like this. So these values of temperature is the normal temperature in a fire in a compartment like that. And the steel melt at around 1,500 degrees. I have here also the degradation and the comparison of the degradation of the yield strength with elastic model. The stiffness reduced much more faster. Here, the thermal properties, the variation of the thermal properties with the increase of the temperatures. And I think this is one of the advantages of this project, because normally in the design we consider the thermal properties at ambient temperature. And in this project, we also consider the variation of the thermal properties, not only in the steel, but also in the protection of in the materials used for the protection of the structure. Okay, and to finalize, some remarks about thermal insulation and flame propagation. We need to take into account first the fire protection measures. We need to use fire resistant materials, as I said, for class A, but we need also to consider fire barriers, fire stop, fire resistant insulation. We need to take into account the compartmentation. Normally, these industrial buildings are as I said at the beginning, they have a large area, but it is necessary to have a compartmentation, taking account the material that we have in these buildings, a division of the structure into fire-resistant compartments, or using fire barriers to prevent the spread of fire and smoke. And it is necessary also a continuous fire modeling and safety system. Okay, thank you very much. Okay, the next presentation will be done by Luís Cordeiro, that is the coordinator of the project. And the presentation will be titled Platform for Calculating and Optimizing the Cost of Industrial and Commercial Pavilions Built with Metallic Structure. Luís Cordeiro is CTO of OneSource. It is involved in more than 10 research projects since 2004, mostly of them in the scope in the field of networking, cloud, and security. And he has an extensive background in these areas of data communication, security, infrastructure management, and virtualization.
Okay. So thank you very much, Professor Naldina. So I will use a little bit your presentation to start my introduction to the switch to steel. So as we saw before, there are these challenges in building these pavilions using steel materials, and we have seen some disadvantages of using steel and how we can also protect the steel to be able to overcome these limitations and to make these pavilions, these steel pavilions, a good solution which brings lots of value besides compared to other solutions. So me, Luís Cordeiro, so I'm from the ICT field. My company is an ICT company, and we have partnered up with the University of Coimbra and NCMM and DISIS to try and develop a solution that can help everyone in planning the development of pavilions using steel and optimize these solutions in a way that can be useful, quick and efficient, and we can allow the user to compare them with other solutions without needing to go into much detail and using very extensive tools. And this is very focused on architectures, on preliminary work. So the goal was exactly to bring a novelty in this field, so everyone is able to properly dimensionate their structures and assess what they can do and cannot do with steel in this type of pavilions. So what are we going to answer? Exactly this. So the optimization of structure. So we need to see what is the most optimal structure. So avoiding people to have extensive background in steel construction, and at the same time to be able to design a proper solution that can fit their needs. To increase the sensitivity of and the ability exactly to do these calculations, and to show that we can lower the cost not only of the construction but also transport, maintenance, and many other aspects that involve a building, in this case a pavilion, and how steel can impact these costs and how we can see real value in this. So the problem, as it was presented before, we have continuous legislation changes. We have legislation throughout Europe, but then we have very specific country focused legislation. And we need to consider this in all the steps of what we are doing. It is really difficult to calculate these structures. So many options, so many types of steel, so many types of solutions. And we tried here to gather all the benefits of all these different options and put them together in a way that we can provide you solutions. You can simulate different options very quickly, and you can find quick and quite efficient results. And yeah, always keeping in mind the compliance, the safety as it was presented before. And again, the application of ensuring that these legislations are properly applied to all aspects of what we are doing. That is really important. And again, the protection for fire, which is one of the main drawbacks of using steel, we can identify in an automatic way which is the best solution for your specific needs, and give you an estimation of that cost. And you can also compare it very easily with other options available, ensure that these options also comply with legislation, and give at the end the power to the user that is making these simulations and analysis. Okay. Yeah, and this is what we call the switch to steel. Basically, an application that you can already download to your mobile devices, and you can make this testing. So that's the switch to steel project. That's one of the key results of the project, besides all the research that was done and gathering information from many countries around the world about all these aspects. So we, as I said before, we target a very specific audience for what the work we have done. So again, we do not compete with very specialized software to do these calculations, which usually are quite challenging to use. They require a lot of know-how to make the simulations and to make the calculations of the structures, of the fire protections and all of that. We want to focus on when those capabilities do not exist, or we don't want to apply them. We want to use more quicker and simple way to simulate this. So we are talking about metallurgical companies, architects' offices, engineering offices, and construction companies. So quite a broad spectrum, but very focused on all of them for different phases of the project, of course, depending on the needs. And you can see that we consider quite an extensive array of algorithms, solutions, and everything inside, which will then be presented later. Here you have the links for the application. The application that was developed, the platform that was developed, is already available for everyone to use. Of course, this is an ongoing work, so we are improving it every day. And what you can see is that you have application for Android, for iOS. You can download the application, and what you are going to do is to define exactly what you need, and then we will process all your requirements and give you the results of what we believe is the best solution for you. Okay, these calculations are not done in your mobile phones because they are quite extensive and they take some time. So you will receive a report and notification that the calculation is done when it is done. Depending on what you need, calculation can go from a couple of minutes to a couple of hours, but it's just a matter of what you have identified as the interest for these details. Okay, so the goal is exactly to do what I've presented before, to have a multi-channel approach for everyone to be able to access the tool and then parameterize exactly what you need and give you the optimizations with different techniques of the structure and also the protections that are needed. Taking into consideration the legislation, as it was said before, and as you can see, characteristics of the pavilions, the fire protection, the transport, the systemic resistance, and the environmental impact throughout all the chain of the building, since the beginning until the end of the building. So as you can see already, there are a lot of innovations here in what was done. We identified these 4 innovation aspects of this work. So the dimensioning of the structures, the combining of different techniques to give you the best solution, which will be presented later in more detail. The dimensioning of the structure, again, with quite different solutions based on characteristics, and basically a very focused solution on pavilions, construction with steel. Very briefly, and my colleagues next will present this in more detail, we have used generic algorithms for some optimizations. The room and elevated temperatures are something that was taken into consideration throughout multiple steps of the process. We use the finite elements methods to some of the analysis and optimizations also, and always considering the error codes in all aspects of what we are doing, of course, to be compliant. Okay, so I'm missing here one slide. So what we are going to do now, instead of me presenting the application with some slides, we are going to have a real-time demonstration of the application. Okay, we will split this into phases. The first one is where we say what we need to build. Okay, and the second one is to show you the result of what was done. We will design a complete step with some predefined configurations. And what will happen is that because that algorithm will take around 20 minutes to run, we will see already one pre-calculated aspect of it. So just switch here. Okay. Oops. Oh. Okay. So here we have our dashboard. So our own, when we enter our application, when you download it, you can use it in the tablet, you can use it in the mobile phone, or even in the future, you will be able to use it in the Windows, in Mac, as an application. For now, we only support Android and iOS devices. You have immediately an history of all the simulations that you have done. You can pick one of these and rerun it with different options. For example, if you want to compare, okay, I want more vents in the or less, and you can compare it, or I want this type of steel or the other one, or some characteristics. You can be evolving simulations, and you always have the track record, the history of what was performed. Okay, so this is our start. We start there by defining the building parameters. So most of the screens you are going to see, we have given you a preset of things that you can use. So you can even, in the last resort, go next without changing anything, and you will see a simulation. But the important thing is to actually assess what we have in each one of them to see the power of it. First one is just to describe your project. It's your own information, so you identify what you are doing. Anytime you go back to that simulation, you understand, okay, this is my simulation with this characteristic and that one. It's for a specific project and so on. So this is just a quick screen that you have. Then we have the characteristics of where we are going to place our pavilion. So we identify the country, the city, the altitude of it, the wind, also the terrain topologies. So many of the characteristics that are critical for the proper assessment, proper optimization of the pavilion we are going to build. Okay, next screen. We have here a list of what we want to simulate, okay? And we have divided this in three main aspects, which, of course, if we say we want or not, will change the next steps. The first one is the structural design, where we have optimization. So we let the algorithm, we let the application decide everything and try to optimize the solution. Or we use the user-defined option where we already say we want this and we want that, and we limit a little bit of what we wanted to do. Of course, the second solution, the user-defined, is quicker because there are not a lot of options to define, but the optimization is where we take some time to give you and to find the best solution for you. Okay? The second one is the fire. As we saw before, fire is critical in this type of pavilions. So we can, at the end, disable this option, of course, but the goal of the application is that we can use a standard option where we will decide exactly what we believe is the best solution. And then we have an advanced option where you will have to define many more parameters to specify exactly what you need. We will use by default in the standard a couple of things that we have identified as the standard, as it says. But this is where you do that choice. And finally, we can even give you an estimate of the cost of each aspect of the pavilion. Okay? And we will see, because we are going to use that option. Next. So, start, of course, we are working with steel. So let's define exactly some parameters of the steel that we want to use. In here, you can switch some characteristics of profile, for the sections, for the columns. So you have some options here available. Not everything is there. We are at the moment limited to a couple of them, but you already have quite an extensive options there. Next. Then let's describe our pavilion. What do we need? Okay. So one of the key things we have to identify is the spans. How many spans we have. And here we are going to describe both the height, the length of the span, and the length of the building. Okay. Of course, when you start changing these parameters, for example, we are already limiting you for the number of spans that you can add. For example, if you select a quite wide span, you cannot build only one. You will have to build 2 or 3 spans, depending on what is needed. And the platform automatically helps you on that to make sure that you are going to a proper solution and not going to something that is not feasible. Okay? So we are going to use these parameters with 2 spans, and then we can even specify different sizes for the spans. Again, the system will help you on that. So next screen. And now we have already identified these spans. What do we need now to do? To identify our openings. Okay? And what type of openings can we have? We have doors, windows, and roof openings. Okay? So how many? In which one of the spans? That's configured there. So we can define a door, for example, and we can define exactly the size of the door, where it's going to be in our building. So we have the front, the back, the left, the right. And of course, this considers also the joint connection between the 2 spans. Okay? We can have doors there or not, depend on what we are defining. Okay? So in this case, my colleague is creating a door there. We can create a window. Okay, we select the door is in the front. Now we have the window on the left. Again, positioning exactly where we need or where we want to have it, because this will have quite an impact, not only on the structure, but mostly on the fire protection. This it will influentiate a lot of the heat dissipation and how we need to protect our structure based on this. Of course, door, windows, and then we have one of the most important for the fire protection, which are the roof openings. Okay, again, we position exactly the openings, how many we want, fully customized, exactly to fit what you need. Remember, I said before that you can build one simulation and then build on top of that simulation a new one, which means that, for example, you can test without openings in the roof, and then you can simulate with openings spread around the roof and assess exactly what is going to be the difference, both in terms of the structure, mostly in terms of the fire protection, but also in terms of the cost, which at the end, most of the times is the most critical one. Okay, so we can continue. Again, we have defined only for one span. It's going to be exactly the same for the other one. So next. Because we enabled fire, we have then a specific screen for fire, of course. And in here, depending on the mode, if it's the standard or the advanced, we will have different requirements for configurations. So as it was presented before, we need to know what is the fire resistance that this type of building will require. So is it just for storage? Is it for people to be inside the building? So depending on that, the resistance needs to be different. Also, the country has different legislation. So we have all that option here. And then we have the type of protections that we want to apply, both in beams, in the columns, and some other characteristics. So go a little bit down. Here we have additional information that we can fill in with regards to the fire protection properties. Again, quite extensive, but if we choose different options on the top, we have different parameters here to define. Also, again, if we selected the fire advanced mode, we would have here in this section many more options to fill in. Okay. Next screen. Now we have the costs. One of our last screens. We have used the average costs for the materials, for the labor that we have identified. So these values are already preset in the configuration, but each one of you can define your own, because each company has a different way to negotiate and has a different values most of the time. So you can define your own costs here and use them for the cost simulation. Okay, and finally, you can go next screen. We have the summary. In here, we can see exactly what we have set. So as you can see, we have a 3D model. So you will play around in your mobile device or around this. You have the building. If you see inside the building, there is still no structure inside because we haven't yet started our calculations. But you already see the openings and how the building is placed to validate it's exactly what you need. You can go to the front, left, no, right visualization just to focus you more there. And then we have the summary, which basically is just an overview of everything that you have selected before. Then we have the final button to select, which is just do your work, calculate everything that I have asked for. Of course, we are going to do this, and this will take some time. So let's go and see this simulation already calculated. Can we? Okay, so we have here the demo, and this is basically the final screens that we get. So we have a summary, and we have now the 3D visualization again. But the big difference is that if we go inside, we already have the structure. So all of this was calculated using all those optimizations that I talked about, and my colleagues will describe in more detail next. And you can visualize everything from this perspective. And then we have quite a comprehensive, okay, we can see only the structure. So if it's easier to identify, you can select the beams and get the details of each one of them, the columns, all of that. And we have the report, which at the end is our what we really need, which is composed of some generic information. We have all the information about the structure. Can go down. Of course, we have an advanced version of the results that is provided, but this is the summary, which usually is the most relevant one. So we have the structure information. Go down. Then we have the fire protection aspect. So what was identified as the optimum solution for the fire protection. And finally, the costs. Again, the costs, we have the steel costs, the transportation, the assembly, the fire protection, and at the end, the total cost. Okay, and basically this is what we have developed in this project and what is now available for you to experiment, to use, and to also to give us some feedback on what was done. Okay, and with this I conclude my presentation. And if you have questions, I think it's better if we address them all at the end. So now, as it is in the agenda, despite a slight delay, we are going for our coffee break, where fazemos o coffee break. Okay, and we will have the next presentation afterwards, after our coffee break. So I think most the attendees in person are already here. Let's start this second phase of the workshop with the presentation that was skipped from the first part due to some delay by my presentation. So we are going now to have a presentation from Philip. I give up. The presentation is entitled Switch to Steel Application, Background Material and Design Examples. Philip is a researcher and lecturer at the University of Coimbra and is part of this research group. His expertise are mainly on the stability of steel structures, steel bridges, and use of advanced programming techniques for the optimization steel structures. Please.
Okay, hello everybody. I will carry on with the background material. So after these interesting parts from my colleagues, I will talk about the background, the theoretical background. Behind every button that you saw in a previous presentation, there is a mechanism, the algorithms that are hidden behind. And I was working on that, so it's time to see what is the scope of this application, what was done in a background. So this is the content of my presentation. It's time to see what is the limit of this application. So it does many things, but there are some things that it's not possible to do using this app. And of course, later I will just go roughly through the algorithms that are involved. So in case somebody is interested in every specific aspect of the design and the structural solver. And then I will show just a simple example how this application, for example, can be used. So the scope of this app and of this project, I think already the Professor Aldina and Luis, they spoke about this. So it's mainly about the industrial buildings or the commercial buildings. When we started, it seemed it was going to be very easy to identify these kind of structures, but then when you start digging into the every aspect of this structure, it turns out to be very complex. So there are many aspects that we had to address here. So the type of the utilization, mainly because of the fire protection, then the different typologies, the dimensional limits, profiles, connections, bracings, and so on. So I'll go just through through each and every one of these aspects, just to understand what is hidden behind the project. So in terms of the utilization type of the buildings, as we said many times, it's mainly the industrial sheds, but also the commercial buildings, mainly based on a portal frame design. So the different typologies are covered in the app. Here you can see several typical examples. And also we identified, this seems very obvious, but in fact it's quite different what kind of rafter you have in the top of the building. So is it just a uniform member? Is it a tapered member with the haunches? Different variable cross sections in an area closer to the column, closer to the apex, and so on. So all of these aspects are something that is really tricky to calculate, especially manually. It's impossible, in fact. And then also there are multi-span buildings up to 4 spans. Then all possible steel profiles that you can think of, hot-rolled, built-up sections, including the class 4. This is something that is not included in many of the commercial softwares. And also you can see that there are tubular sections. So pretty much everything that is used in a building, in a design of this kind of buildings. Then also the connections, the base of the columns can be fixed and pinned. Then the corners, so this connection between the rafter and the column, it's a hunch that we also calculate some pre-design of the connection. So it's not fully a full design of the connection, just a preliminary. And then also there is at the apex similar type of connection. Then the bracings, all possible configurations of the bracings and all possible types of profiles, mainly tubular cross sections. Then the steels, the carbon steels are used in this project. So the conventional steel grades, not the high strength steels or stainless steels. And then also the fire protection materials, we try to include here all the relevant fire protection materials that are currently available on the market. So including sprays, mortars, plasterboards, and paints. So this is the scope. This is the scope of the project. But of course, as I said, there are some limitations. And first and foremost is the typology. There is no trusses, at least not in this version of the project. So maybe in the future we will have Switch2Steel plus or something that will include also the trusses. It's not difficult, but it takes a little bit exercise to play with the optimization of all these profiles. And also some like a very specific geometry such as arches. It's also not involved in this project. Then the dimensional limits, we put some limits in terms of the dimensions, something that is found in the literature. It's not in terms of the computation that we cannot go beyond 120, just that it doesn't make sense to allow the user, some kids, to put their 2 kilometers, the length or the height of 100 meters. So this is something that is commonly used for this kind of buildings. And in terms of the loads, I will come later to the loads that are included, but the cranes and the loads from the cranes are not involved. So this is the warehouse buildings with the storage. So the cranes are not involved. And also not explicit calculation of the foundations. So only the upper structure of the steel. Then the calculation algorithms. Here I would divide all the calculations in 3 groups: the structural solver, the structural design, and the structural optimization. The solver is probably the best feature of this tool because we have our own solver. It's a linear solver, and for this kind of buildings with a very severe stability issues and with the variable cross sections and some very specific problems and aspects, it's almost impossible to use some simple databases and so on. So we have our own solver that calculates precisely what is the response of the building. Also, for this kind of buildings, as you may assume, it's really important to take into consideration second order effects. And of course, for that, you have to have your own solver. So all of these aspects are covered both at the ambient temperature and at the fire design. So this is just a flow chart of of what I just said. The client or the user of the app needs to give us the inputs. Cordeiro already showed that. And then we somehow split the calculation with the flux in two parts. The one is the ambient temperature, so on the left side, where we optimize the structure without considering the fire at all. And then at the same time, we have like the back calculation of the fire curves. So this is really important thing. And then these two results join in an optimization according to fire. So once we have the structure and once we have the fire, the advanced calculation of the fire, we can finally optimize the fire protection. And of course, there is the output. So the biggest effort here was in these two steps where we include the solver, the design, the genetic algorithms in the first case, and then the fire protection material optimization in the fourth step. So let's say something about each and every part of these algorithms. In terms of the structural solver, it's a linear elastic solver. So it's a finite element based using the beam elements. We use the Python code here to write this code, and then what is also the advantage is that the load combinations and the load actions are automatically calculated for you, so you don't have to really go into the code, do the calculation of the coefficients, especially for the wind. This is really handy, and also automatically we generate the load combinations. So this is something that is done in a matter of seconds, and so this is, I think, a great advantage, because in the beginning I remember I had to calculate and check everything manually. For one of these, it takes like sometimes a whole day, or I don't know. So, and then there are some other features here, such as second order effects that I already mentioned. This is really important, and for that you need to have the solver and some extra possibilities such as eccentricities, semi-rigid connections, and so on. So the solver is, as I said, finite element based, using the displacement methods. So we build the stiffness matrix of the whole system. And then such a routine, it's very convenient for the Python code or any other language. We use the Python. The objective of the solver is, of course, to get the internal forces, reactions, and the displacement in every node. And so from that point, using these results, we go to the design. In terms of the load actions that are already involved in the solver part, we have the permanent actions. Then we have the imposed loads. So this is pretty much based on the Eurocode design, the imposed loads on the roof. Then we have the snow loads. This is the map of Portugal, but we also included from all the relevant and countries in Europe. Pretty much we try to have a database of all the countries. Then for the wind load, it's pretty much the same story. The wind speeds that are involved, there is a database, and we try to cover for every country almost what is the wind speed. And of course, all these calculations are carried out for you automatically. So especially these tabular values, the coefficients and everything, it's applied automatically on the structure. Then the load combinations for ULS, so for the ultimate limit states and for the serviceability limit states, are also, as I said, calculated automatically for you and applied on the structure. Other features, as I said, I explicitly included here the second order effects using the stationary potential energy principles, and so we can calculate the critical force, and then the second order effects are involved and implemented using the amplified sway moments. Then the semi-rigid connections are also included. That's a possibility also if we want to play a little bit with the rigidity between the rafter and the column or any other part of the structure. You can adjust the stiffness of the connection. Then this was the solver. Once we have all the results, we can go to the next step, and there is a structural design. The structural design, I'm not going to go into detail because this is very basic stuff from the Eurocodes. So for the ultimate limit states, we have to do the classification. As I said, we cover all possible classes, including the class 4. The cross-section checks, of course, on the cross-section level, the verifications, the member verification, stability, which is probably the biggest issue for these kind of structures, and then the connections. For the SLS verification, we verify the displacements, vertical and also the horizontal ones. Then some extra features. For example, these corners of the portal frames is something that looks obvious, but in fact, it's a really tricky calculation behind. So it's a double flange cross-section, and then to consider all possible positions of the neutral axis, especially if it's a class 4. it takes some effort to do that. So this is not done, of course, automatically. Can be at the corners of the frame or in the apex, as you can see on the top of the slide. Then we also have the tapered members. This is one of the reasons why we opted for our own solver. And of course, you can vary the thicknesses along the length to optimize. In some cases, you can have the length up to 60 meters. So it's really the point of these structures is really to consume the least material possible. And for that one, you need to have the proper solver to calculate the stresses and also the forces in every part of the structure. So this is done automatically. And then there are some specific aspects for these kind of structures. So we have the purlins on the top of these buildings, and they can act as the lateral restraints. But if you have the wind, then the bottom flange, which doesn't have any purlin, is exposed to the compression, and there is a problem with the stability. So we use there is no such calculation provided in the codes. So we use some literature from the King and SCI publications to calculate this kind of phenomenon. So the point is that even if the top flange is in tension, there is some benefit from the purlins, and this has to be calculated somehow. And in these SCI publications, we have this method. So this is also included here. Finally, there is a class 4 cross-section included. This is something that is quite simple if you have just an actual force or just a bending moment for the symmetric cross-section. But in many cases, we can have, especially for the tapered, monosymmetric cross-sections, and then the problem turns out to be a little bit more complex. So this is all involved in this calculation. And then last but not least, there is a fire design. So our methodology that we applied here is pretty much based on a typical method that is used. We have 2 steps. In the first part, we treat the fire load. So we calculate the fire curve. There are 2 options, as you saw in the app. There is a standard curve, and there is the advanced curve, which is the natural curve using another software that we linked to our platform. And then the mechanical actions are included through the load combination, accidental ones from the Eurocode. So this is the fire load, let's say. And then in the second step, we have the structural response and the structural design according to the respective Eurocode 3.1.2. So this is also done. And when I say the fire curves, there are many fire curves. There's ISO standard curve, there are some parametric curves, but in this project, we use very sophisticated way of calculating the curve, this red one, which accounts also for the decay of the curve, which is really important. Significant savings can be made in a fire protection if we use this kind of curve and not the ISO curve. And so any possible number of the compartments and the openings plays here a significant role. And this is what we are doing in a matter of a couple of seconds. So this is the advantage of the tool. And then the second step is the application of the accidental loads according to the code. Then we have this heat transfer according to the code for unprotected and also for the protected steel cross sections. And then in the last step, once the steel frame is heated, let's say, we have the decline in properties. And this is important on the level of the solver because the properties changes. And then we have the matrix of the system also varies with the changes of the modulus of elasticity. And then in the structural design, of course, like with the new properties of the steel, we calculate the resistance of the elements. According to the code, as you know, maybe there are 3 ways to verify the fire resistance. We use in this project resistance domain. So it's pretty much the comparison between the resistance and the applied load in the terms of fire. And then the third part, the third group of algorithms is the structural optimization, which is applied, as I said here, in this phase using the genetic algorithms and also for the fire protection. So the genetic algorithms, this is some slide with some technical terms and the terminology that's used for the explanation of the genetic algorithm. But the goal of this method is very simple. It's something that is used for many decades now. So the goal is to imitate the Darwin's theory of evolution. So from the first pool of structures, you choose the best species, and then you go to the next generation, and only the best species are surviving constantly until we are happy with the convergence. So pretty much this is what takes some time. So depending on, especially for the built up cross sections where we have so many variables, this can take some time if we want really to be to choose the best solution of all. Of course, we can a little bit relax this to reduce the time, but then we cannot guarantee that the solution will be absolutely the best. So this is just the compromise between the time and what we want. This is the mathematical description of the genetic algorithm. So there is a fitness function, which is the quality of every specimen, and this is obtained by either maximizing or minimizing some, let's say, weight and costs. For us, it's obviously the minimizing the cost and weight, and there are some main constraints, which are the ULS and the SLS verifications. Finally, the genotype is something that is really important to see what we can optimize, what are the variables, and what are the key aspects that we want to attack here. And as I said, for the built-up cross-section, there is a really wide range of parameters, because you can technically optimize every possible thickness, and then it takes some time. So this is the genetic algorithm involved. And now that I mentioned also the cost, for the cost of the frame, we currently calculate the cost of one frame, because to calculate the cost of the entire building, there are so many unknowns that we didn't want to just specify, because as Cordelia said, every company almost has their own panels for the roof, different things that are not covered in this project. So we don't have the database on all the panels that can be used in the industry. So we wanted to specify here that there is a limit. We calculate the cost of what we calculated, and then the rest is something that every company can add as some extra cost. So what parameters we considered is the material properties and the cost of the steel and the fire protection, because especially the fire protection is something that is pretty much hidden. You cannot find almost the prices of these things. So we just allow the user to define his own price. The transportation, based on the distance, how far is the factory where we're going to produce some elements, and then the assembly costs, some basic parameters we consider here, such as labor cost and the crane that is going to be used, what is the effective utilization factor and the crane span, and so on. So there is an algorithm from the literature that we followed here for the calculation of the cost. And now finally, just to show one simple example. So this is a one-span building. You can see here a couple of characteristics of this frame, such as the location, what is the geometry. So one span with a length, I cannot find the mouse here. Yeah, so yeah, you can see here the 25-meter span. Then there's the height of 7.5 meter of the column. The depth or the length of the building is 100 meters, and there are some loads. What is the material? 355 steel, and so on. So this is the geometry of the building. So this is very simple to apply using the tool. So all these inputs you can literally on your mobile define in a couple of seconds. What is the location? What are the material? What are the profiles? And finally, what is the geometry? So this is what you saw in a previous slide. It is already defined here as the input. The load combinations. This is just a schematic representation of how many combinations are considered in this case, as many as 14 different combinations with the wind, lifting, pushing down, wind, all possible combinations from the Eurocode that you can imagine, including the SLS verification. Then, for the sake of this presentation, we compared our results with the finite element method. So using the Abacus model, this is done in a collaboration with Laim, our colleague Luis Laim, and also with Pega. She's going to present her work, I think, more in detail about this. I'm not sure if that's your presentation, but generally we carried out much more sophisticated calculation here for one load combination only. And okay, this is the buckling behavior, and this is the ultimate state, so the failure of the frame. And this is the shell model. So we try to really have the imitation of, let's say, reality, just to see how far we are with our tool. And here you can see some comparison of the results. Here in this table, you can see the results of our tool and of the finite element methods using for the ULS combination and SLS combination. But this is only for the first combination. And as you can see, the difference is up to 10%, which is somebody may say it's significant, but this is much more sophisticated tool. So according to the Eurocode, let's say, and using our tool, it's more safe, which is expected result. But then when we start comparing a little bit the time spent for the obtaining of this result and of this one, it's almost incomparable. Because for the switch to steel, the modeling, let's say, takes 5 minutes for somebody who never used this tool. I believe it's less than 1.5 minutes to run the analysis, especially for the user-defined, which was the case here. It's also a matter of 30 seconds maybe. And then for the shell model in Abacus, you need, if you're very experienced with Abacus, you need up to 2 hours maybe to do this. And then for the calculation, only for one combination, it takes a couple of hours. So if you want to do 14 combinations that we did, this would take probably, I don't know, the entire weekend or maybe 3 days, or I don't know. So this is the compromise, and I think the 10% difference is something that we can always accept with a couple of minutes calculation. Then the second phase, this was at the ambient temperature, the comparison, and then there is the fire load. We used here the standard ISO curve just for the sake of the comparison. In our tool, you can easily here define what is the fire resistance. For example, 60 minutes we chose in this case, the standard curve and some fire protection here. And as you can see, when we compare the fire results, this is done by Vega, the critical temperature is almost identical. There is absolutely no difference, which is not surprised because the steel, it's very difficult not to guess the correct critical temperature using any tool, because at the 60 minutes, this is almost the rule. But also the fire protection, when we started optimizing the fire protection with the two techniques, the difference is almost negligible, so less than 5%. What is the best part about the tool is that you can define much more advanced fire curves and the fire calculation using, you can vary the properties of the walls, of the floor, of the roof, of any material. You can vary and place as many openings that you want to assess this, how it impacts the calculation. You can choose any of the fire protection materials, how many sides of the columns or the beams are attacked. So there's so many options that we included in this part. And then here you can see just a graph of the comparison. The red triangular point is the finite element calculation. This dashed line is the fire protection. So yeah, I didn't say, but this is the fire protection in millimeters on this axis, and here is the fire resistance. So for the 60 minutes here, you can see that the finite element using the first, let's say the most severe combination, tells you to use 6.2 millimeters. And then using the tool in a couple of minutes almost, you can do the optimization of the fire protection and the strategy, how you're going to protect your building. And then, as you can see, we can go down up to 2-3 times more economical solutions. So this is, I think, the biggest advantage of this tool, that in a matter of couple of minutes, you can really calculate the fire protection. So this is the good thing. And I think that would be all from me. So thank you very much. If you have any questions, we can discuss now or later. Thank you.
Comparison with finance element and the application that we use. And I want to know what is basically finite elements. What is the base method used in the application?
No, I already said we use the linear elements, the beam elements, linear elements. So, and that's the surprise that the difference is only 10%, even if we with Abacus use the shell elements. So, yeah, exactly. So the beam is in our application, the linear beam elements, and then in Abacus we use the 3D, let's say, shell model. And I think the difference is not significant because with such a big spans and with such a small cross sections, the structure is pretty much 2D. So the third dimension is almost irrelevant. You're welcome.
So thank you very much. So we are now going for the next presentation. The next presentation is titled Optimization of Fire Protection in the Design of Frame Structures, and is going to be presented by Pega.
Hello, everyone. Please introduce me. My name is Pega, and I'm a PhD student, and I was working on a part of Switch2Steel project. And the topic I'm going to talk about with you today is the optimization of fire protection in the design of steel frame structures. Let's start with a brief introduction about the steel frame structures. They have a wide range of application in the construction section, and because this is due to the exceptional properties of steel compared to other construction materials. Some of these properties, as you may know, are the highest range to weight ratio and very high durability compared to other materials. Okay. Here you can see some application of the steel frame structures like commercial, industrial, residential, and etc. We're going to focus more on the warehouse building as it's selected as a reference case study here. But fire in these steel frame structures can be dangerous because of a rapid increase of steel temperature as a result of high thermal conductivity and high section factor. This sudden increase of steel temperature can lead to a decline in structural stability and making these steel frame structures to have a low fire resistance and compromising the competitiveness of the steel frame structures in the frame construction section. So the question is, what is the solution? Fire protection materials can be one of the solutions for that. And gypsum-based fire protection coatings are used in this study. Because the reason to choosing them is because the effectiveness in improving the fire resistance of the structural steel members have been already proven to us in some research studies carried out in the University of Coimbra here. And especially when high fire resistance rating were required. These fire protection mortars, they can be used in different ways like pours, sprays, and mortars. And they are composed of, this developed gypsum-based mortar is composed of light-weight aggregate, expanded pellet, and gypsum plaster. And it has a very low thermal conductivity and higher very good specific heat capacity that makes it a very perfect solution to protect these steel frame structures against the fire. So what's the objective of this study? The objective is evaluating the numerical fire behavior of these structures protected with these fire protection mortars using three-dimensional finite element models developed in Abacus software and calculating and optimizing this fire protection for industrial and commercial metal buildings and presenting the hypotheses and parameters taken into account in the numerical modeling to have an accurate and efficient thermomechanical response for these fire protected steel frame structures, and study the influence of some crucial parameters on the fire protection optimization and critical temperature of these structures at high temperature, like lateral restraint, thermal properties of fire protection, and fire action. And finally, comparing the finite element result with some results obtained from Switch2Steel computational tool that Philippe talked about that in previous presentation. For this work, an example of a two-pitch steel industrial shed located in Figueroa da Foz is selected as a reference case study. And the span of the main portal frame is 25 meters with the column height of 7.5 meters and this roof slope of 10%. It looks like similar to you because it was in the previous presentation. And the required fire resistance is 60 minutes, and the main frame is built of hot roll profile. For the column is HEB 260, and for the rafter IP 450. And what else? And the load is 2.2 kilonewton per meter over the rafters, vertical. And the finite element model of half of this portal frame under high temperature were developed with respect to symmetric rule in Abacus. And the structural elements are shell elements, and with mesh sizes of 25 millimeter across the cross section and 50 millimeter longitudinally. And three different analyses named thermal, linear buckling, and nonlinear geometric and material static analyses were sequentially carried out to assess the fire behavior of these structures protected with such mortars. Here you can see some. I think it would be better to use. Do you know how can I use pointer? Yeah, I think I can. These are some of the results taken from Abacus about from the different analyses that I mentioned in previous slide. And for the local and global imperfection, the maximum magnitude of L over 1000 and width over 200 were implemented in the finite element model to the structural analysis as recommended in Eurocode. And here you can see the steel mechanical properties at elevated temperature based on the Eurocode that is used in the applied to the finite element model. And about the fire protection mechanical properties, experimental results available in literature and some other obtained from the test carried out here were adopted in finite element model. These figures show the numerical results of the thermomechanical analysis on the structural component of the portal frame, I mean column and rafter, that is protected with fire protection mortar when fully lateral restraint are applied and when it's subjected to 60 minutes of ISO standard fire care for different fire protection thicknesses. And the optimum protection thickness and the critical temperature is shown in this table. For the rafter, it was around 5 to 6 millimeter, and for the column, it was 5 millimeter, and also a comparison with the corresponding values obtained using the Switch2Steel tool has been made. And no significant difference was observed, and they are comparable. And now, in this, in the next step, we remove the lateral restraint, which are shown in this figure, for the cases that the palings are not protected against the fire action. And the optimum thickness of the fire protection and critical temperature on the rafter and column are obtained for this case without lateral restraints when it's exposed to the ISO standard fire care. And these figures show the impact of the removing lateral restraint on the optimum thickness and critical temperature of the steel elements, when 60 minutes fire resistance is required. And it's shown that in the table that the optimal fire protection thickness is increased until 2 times. So this shows the crucial role that this removing lateral restraint plays on the critical time and maximum temperature of the elements and fire protection thickness. Another parameter that can have a significant impact on the structural steel temperature prediction and the fire protection optimization of these portaframe is considering thermal properties as a function of the thermal properties of the fire protection as a function of its temperature. That is the case in reality. The thing that the Eurocode disregarded that, and the thermal properties of these fire protection mortars, they are, as you can observe here, they were non-linear with increasing the temperature as a consequence of its temperature level, water content, and heating rate, porosity, and thermal expansion, and etc. So the figures that highlights the influence of considering the thermal properties of fire protection as a function of temperature is shown here, and there is, as you can observe here, there is a decrease in the calculated optimum protection thickness compared to the previous case, and the critical temperature it's decreased a little bit, and the frame here is again exposed to the ISO standard fire care for 60 minutes fire resistance. So the next step, the next parameter that we consider was the thermal action. You know, thermal action plays a crucial role in assessing the structural fire behavior of the C-frame structures and optimizing them. So in this section, instead of using the standard time temperature curve based on Eurocode and ISO 834, that assumes a uniform time temperature relationship for gases surrounding the element. We use the natural fire curve, and this model accounts for the effective heat flow transfer through the fire spread into the element, and to predict the development of the plumer in the warehouse, the two-zone model in the CFast modeling software was developed, and this approach also considers the localized fire above the beam, and it assumes a warehouse without roof opening. And you can see here the fire protection optimization for when the plumer is considered instead of a standard fire curve, ISO standard fire curve. And the thermomechanical results in terms of the fire protection thickness and critical temperature are shown here. And they are also compared with the with the standard fire curve, with the corresponding standard fire curve. And you see, we can observe that for the natural fire curve, there is a significant difference in the optimum fire protection thickness, and it highlights the crucial role of the thermal action in the fire protection optimization of these C-frame structures to ensure a safe and optimal solution for risk mitigation. And regarding the significant importance and significant effect of accuracy predicting the thermal action and fire scenario and fire protection optimization of these structures, another scenario is taken into account. In this scenario, the rafter is exposed to the same plumer curve, but the column, the lower part is exposed to the colder time temperature curve, and the upper part is exposed to hot air time temperature curve. And these curves, they are also estimated using the CFast programming code, and the results. I just got the results, so I didn't have enough time to put that here, but the result indicated that maintaining the same fire protection thickness for the rafters, that was, I mean, the optimal fire protection thickness for the rafter, it was around 70 millimeter. The column doesn't require that much fire protection by considering this fire scenario. It was the optimum fire protection thickness for the column. It was less than 5 millimeter. That was not too much considerable. And as a summary, a comparison between the thermal and thermomechanical results obtained from the finite element simulation in Abacus and Switch2Steel show that the Switch2Steel tool proves to be a reliable tool for fire design of the steel frame construction, and it also helps to reducing the computational time in a steel frame construction. It's exactly the same that Philippe told to us in previous presentation, and it's important to consider the real influence of the key parameters such as the lateral strain and fire design scenario and thermal properties of the fire protection into the account, and this factor, because these factors they can have a significant impact on the amount of the protective material that we're going to use in the steel frame structures to protect them, and neglecting them may lead to have an inadequate fire design and compromising the competitiveness of a steel frame construction and jeopardizing overall safety. And this reference, and thank you so much.
So based on the agenda, we are now going for our final presentation. So in this case, our presentation will be the behavior of steel pipe racks subjected to localized fires, and it will be presented by Professor Nicola Tondini. He is an associate professor of structural engineering at the University of Trento, Italy, and in the last 10 years he has been involved in research behavior of structural systems subjected to accidental actions like earthquakes and fires. So I pass now the sharing for Professor.
So thank you very much for the nice introduction. I share the screen. Can you see my screen?
Yes.
Okay. So thank you very much also for the invitation of this nice and interesting workshop. So today I'm going to present some results that we performed on some case studies of steel pipe racks subjected to localized fires in a fully probabilistic way. So here, this is the problem statement. So I mean, we can have in some industrial plants, petrochemical plants with hazardous substances, we have some leakage, loss of containment that can lead to fires in the industrial plants. They are quite common, unfortunately, and then can of course lead to structural failure, to also blasts, domino effects that of course can also affect the nearby community, as also Aldina said in the first presentation. This is an example on this slide that is a fire that was ignited by the Tohoku earthquake in Japan in 2011. And here there are other cases of accidents that were involved in industrial plants where there were some fires. Of course, if the plant there is some storage of hazardous substances, they can also have some blasts, for example, high carbon fuel. And as we can see here in these pictures, when we have supporting structures like pipe racks or tanks, we may have some structural failure, and then they can be impacted by these fires that most of the times, because they happen outdoor I mean, they are localized, and though they can be quite large. Here there is the outline of my presentation. It's just one slide about structural fire engineering. Some descriptions of the localized fire models that are available in the code and in the literature, the description of the case study, and how we built the probabilistic fire demand models in order to derive the fire fragility functions that we can assess also the structural capacity of the steel pipe rack in a fully probabilistic way. So here there is some steps that we have to conduct in order, I mean, to check a structure under fire. Here, the first step, of course, is the fire modeling that can be done by means of nominal fire curves or by means of natural fire curves that, for example, parametric curves that are the simplest that we can find in the literature and also in the code, but then we can use also zone models, field models, also CFD, or localized fires models that we can find in the literature or in the code. Then, of course, we have to perform the thermal analysis, so that how to compute the thermal field in our structural elements, and the mechanical analysis afterwards that can be done with simplified methods or finite element codes. Here, there are some also protection strategies that we can apply. For example, active fire protections, venting systems, smoke curtains, sprinkler systems, or passive fire protections such as for the concrete encasement in these concrete composite structures, intumescent paints, sprays, or boards. And in the end, how can we check a structure? Typically, it is done according to Eurocodes or codes that are based on the semi-probabilistic approach. So there are some characteristic values that are derived by means of probabilistic analysis, but in the end, what we perform is a deterministic analysis. Otherwise, we can employ a fully probabilistic approach where the uncertainty of the parameters are explicitly used in the structural check. Here, for example, it is so with probability distributions, and then we can build also fragility curves. Let's start with the localized fire definition. So typically, when in compartments, the flashover is unlikely, or in the initial phase of the fire, as Aldina said in the first presentation, in large warehouses or commercial buildings, the fire load is such with respect to the size of the compartment that we can have a very non-uniform distribution in the building. So localized fires can be also a source of hazard in this kind of structures. For example, in open car parks, also when in this case when there is some cars that burn, or here there is other examples can be also like airports halls or like a rail station. And here also is another case that can occur. This is a truck that burns underneath a bridge. Here, the modeling of localized fires can be done by means of analytical models that are typically simplified. Some analytical models, as I will show later, can be found in the standards, particularly in the Eurocodes, or we can use some numerical modeling. For example, computational fluid dynamics, that of course is much more demanding in terms of computational burden. Here, it is what is inside the Eurocode at the moment in the present form. So the localized fires are treated in Annex C of Eurocode 1, Part 1.2. Basically, there are two models. The first one is based on the ASCII correlations that can be used in order to predict the flame length and also the temperature along the localized fire axis. And is typically used when the flame does not impact the ceiling. Whereas there is another correlation that is implemented in the present form of the Eurocode 1. It is the Hazemi correlation that allows to compute the heat flux received by a structural element at the ceiling level. And it is typically employed when the flame impacts the ceiling. But so this is used, for example, in open car parks. The Hazemi model when we have beams at the ceiling level. So typically in car parks, the interstory height is quite small in order to optimize the volume and the number of floors. And the ASCII correlation is used when, for example, there is a column that is engulfed into the fire, but the Eurocode lacks from models that can predict the heat flux received by vertical elements such as columns that are outside the localized fire, and so they are not engulfed into the fire, where the main heat transfer mechanism is radiation. So it was 8 years ago. There were some calls for project teams in order to revise the Eurocodes. I was one of the members of the project team of Eurocode 1 Part 2, and one main task was to revise Annex C in order to try to fill this void, this gap. So in the literature, there are already some models that are able to predict the relative heat flux received by a target given by a localized fire. There are simple methods that you can find the point source model, the correlation, the simple Shockley-Baylor correlation. There are more detailed methods that typically they use the view factors. So in terms of the computation, they are a little bit more demanding, more sophisticated in this kind of way. So there is Shockley-Baylor also developed a more sophisticated method, and also Moudin method. Moudin method is also included in some American standard and NP FA 555. And also the Locafi model that was developed, let's say, almost 10 years ago in RFCS project, a European project. So why there was this need to develop a new model? So there were like these models that were already available in the literature, and why there was, this development of that ended up in the Locafi model, because the other methods, there are some, of course, since are the analytical methods, there are some limits in the application field. So what we were looking for, it is a model that can be used in all ranges of heat fluxes. For example, the methods that I mentioned before, they are not valid in some, or not very accurate in some interval of heat fluxes, or they have a low, or they have a high variation in the data. And so we wanted to develop something that had a low variation in the data and also safe without applying safety factors. We wanted also to model something that can estimate the heat flux on the four faces that compose the cross-section of the column, and not only the target that is directly impinged by the heat flux. And also we wanted to exploit the localized fire correlations that are already implemented in Annex C of Eurocode 1 Part 2, so the ASCII correlation, for example. Here, for the Locafi, I'm not going through, the Locafi model in detail, but here are these link, there are some documents that there is information about it and how to use it. Here, in this work about the behavior of steel pipe racks, we implemented the low-café model that was included inside the finite element thermomechanical model Sapphire. So in this case, basically, the localized fire is approximated with a cone, and the cone is discretized in many different surfaces, and then each surface basically radiates away the heat flux, and the temperature of this surface is based on the Esky-Stat correlation. And by means of the integration of the U factors, I mean, we can predict the heat flux received by the column, by taking into account also the distance of the column with respect to the fire, and also the orientation of the column with respect to the fire, and also by taking into account any possible shadow effects. Here, there are just a couple of slides of the validation of the low-café model that was also performed after the RFC's project low-café. This was made in Paris. This is a large fire. It is up to 31 megawatts within a hangar. And then here you can see that the curves are basically the prediction given by the low-café model, and the points are what was measured in the test. So you can see that the relative heat flux is always higher for the low-café model. Here there is the description of the case study that we used. So it is, an actual case study. It is a refinery that is located in central Italy on the eastern coast. Here we had the data of this supporting structure close to the tanks, and here we had some this pipe rack. There are many pipes on it. The structure is not protected, so we of course simplified a little bit the structure. So the structure is a moment resting frame with respect to the short span, whereas it is a braced frame with respect to the longitudinal direction. Here are the loads that we applied to the pipe rack, that were estimated, of course, based on the liquid passing through the pipes, and some operative loads that are applied also during the working phases of the steel pipe. Here, so what, since we performed an analysis that wanted to include explicitly the uncertainty of the parameters, we had to decide, what were the main relevant uncertain parameters. So we decided to include the fire in terms of the size of the fire, so the diameter, the type of fuel. We decided to use different fuels, and of course, based on this choice, we had some uncertainty in the heat release rate, and also of the position of the fire with respect to the structure. And we included also, this is on the fire side, and on the structural side, what we included is the steel material properties, so uncertainty mostly in the yield strength, and how the yield strength varies with temperature. Of course, there are other parameters that can be included, for example, loads. In this case, loads were not kind of well defined, so this is the reason why we didn't include the variation. And the wind also can be really a source of main variation, and then that can impact also the structural behavior, but in this case, we didn't include it. Here we considered 4 cases where basically with increasing variability, let's say. So in the first two cases, we included the diameter of the fire that was in a uniform distribution. So with the same probability of occurrence of the different diameters. And in the first case, we used the deterministic yield strength, that is nominal, so the characteristic value. In the second case, we introduced the probabilistic the definition of the steel yield strength and how it it varies with temperature. And in the second and the third, basically there are 2 different cases where the fire diameter is based on the type of leakage that we may have in a petrochemical plant. For example, we may have leakage from the tank or from the pipe, and this can lead to a different, let's say, phenomenon in order to predict the diameter of the fire. Here, for example, this is how we compute the diameter of the fire based on the leakage from the tank or from the pipe. Here, the driving force of the determination of the fire diameter is the hydraulic pressure. Okay, and then so we use the fluid mechanics concepts in order to determine the diameter of the fuel that leaks from the tank or from the pipe. That is based, of course, on different parameters: the height of the liquid, the diameter of the tank, where the diameter of the hole, the length of the pipe, where the hole is with respect, to the height of the fuel. So this kind of all these parameters were considered in order to derive these probability distributions of the fire diameter based on the liquid through a hole from the tank and the liquid from a pipe. And also we used only diameters that were kind of steady in time, in the sense that in order to be meaningful from a structural point of view, we wanted some diameters that can at least last for 60 minutes. Otherwise, from some parameters, as you can imagine, as soon as the level of the fuel drops, we can have the diameter of the spilled fuel can vanish. And also we used some steadiness criteria in order to estimate some diameters that can last at least 60 minutes. And here in the case study 2 and 3, we used really these distributions, and then we used the Latin hypercube sampling in order to sample all the values. Here, for example, it is case study 0 and case study 1, so where there is the uniform distribution of the diameters. We used 11 diameters from 5 to 30 meters. Here, the distances from the structure from 0.5 to 6 meters, and also 7 fuels. With different, of course, properties, heat of combustion that can lead to different rate of heat release. Here, this is an example on how the thermomechanical analysis about the outcome of a thermomechanical analysis. Here is a heptane fuel with fire diameter equal to 20 meters. Here you can see the deformed shape of the structure, and here the thermal field in the columns. Of course, there is a large thermal gradient, of course, in the structural element because of the localized fire. So to build up the probabilistic framework, we had to decide to the intensity measures that can characterize the severity of the fire, and also the engineering demand parameters that can characterize instead the structural response. Then we applied some methods in order to build up the fragility functions, and then also we established the efficiency, the sufficiency of our probabilistic models. So here the intensity measures that can characterize the fire severity. For example, of course, some of them are quite straightforward. So the diameter of the fire, the structure fire distance, the rate of heat release rate, also L/D, which is the fire position with respect to the fire diameter. But others are less straightforward. For example, this is the maximum average heat flux impinging the structure. And so we analyzed all of them they are not relevant. I mean they cannot be found at the beginning in the literature. So we had to think about them. And then, of course, there are, for example, L/D is a function of the diameter and to the structure fire distance. And the heat flux here, the maximum average heat flux impinging the structure, was computed according to the analytical low-caffeine model. For the engineering demand parameter, so that characterize the structural response, what we considered, so the interstory drift ratio, for example, the axial load in the structural elements, bending moment, the maximum average temperature in the structural element, or the average temperature. What we found that relevant for this case study was the interstory drift ratio, because it is independent from the fire scenarios. Is also quite easy to evaluate, and it is a global parameter of the structure. And also we could relate it to some damage states deriving from the seismic engineering parts, for example, for the FEMA 356. Here, the probabilistic framework was built up by means of cloud analysis, that in this case, the engineering demand parameter is assumed to follow a log normal distribution when it is conditioned on the intensity measure. And in the log space, basically, we can apply a regression, a linear regression, in order to compute the probabilistic demand model. Here, for example, in the end, what we would like it to build up the fragility functions in order to see the probability that engineering demand parameter is larger than a limit state when it is conditioned on an intensity measure. So we took, as I showed in the next slide, two limit states that are related to life limit states and also to collapse limit states. And here there is an example of fragility curves that I will go more in detail later on in the presentation. Here it is the structural analysis results of one case study. It is case study 0. And then here in the green one, there are the life limit states that so the interstory drift ratio that are higher than 2.5%, which means that it can be related to life safe limit state. And here this 5%, which is very close to the near collapse. And then we can build up the fragility functions in this related to the two limit states. Here are the probabilistic demand models for all intensity measures that I mentioned before for the 4 case studies based on the interstory drift ratio. Here, what we have also to perform is to check the efficiency, the sufficiency of our probabilistic models, in the sense that the efficiency, so our intensity measure can be considered efficient when there is a low variation between the predicted engineering demand parameters and the actual engineering demand parameters that are based on our probabilistic demand model. And when the load dispersion is less than 0.3, we can this intensity measure can be classified or qualified as efficient. And then there is also a sufficiency requirement. It is when the structural response, so the engineering demand parameters to the demand, doesn't show correlation in the parameters that can define the demand. In this case, the sufficiency was determined relatively to the intensity measures that we considered. So here we use an information theory concept that can be found in the literature. And here you can see that the highest information was given by the heat flux, the maximum average heat flux received by the structure. And there was also another intensity measure, but I'm not going into this. And also the L over D, that is quite straightforward also for practitioners to understand. So in the end, here you can see the different intensity, the fragility curves for the two limit states. Here for the maximum average heat flux received by the structure, and for the L over D intensity measure. Here you can see that this is the gray zone. It means that when L over D is smaller than 0.5, it means that the column is in part engulfed into the fire. So in this case, it is this intensity measure would not be relevant for our analysis. This is the reason why this is this gray zone. And here, whereas this the fragility functions that are built for the 4 different case studies for the heat flux, what we observed at, of course, when we consider the nominal characteristic value of the yield strength, the probability of the interstory drift ratio to overcome our limit state is higher, because of course we use a characteristic value, so it is 5% per time. Whereas when introduced the uncertainty in the steel yield strength, also the probability of exceedance of the limit state is lower. And then of course, if we consider more uncertain parameters, I mean, we have this probability of occurrence of the exceeding is lower. So here, for example, the case study 2 and case study 3, most of the times provide the lower probability of exceedance of the limit state. And then also it can be used. So to finish, I hope that was more or less in the 20 minutes. So this is the conclusion. So we developed a probabilistic fire demand model for a steel pipe rack exposed to localized fires. In this case, in this presentation, I only showed the fragility fire function that were developed by means of the cloud analysis. We used also the multi-stripe analysis. The maximum transversal interstory drift ratio was found to be the most suitable engineering demand parameter. And also in terms of intensity measures, the maximum average heat flux impinging the structure and the diameter, so the ratio between the fire position and the fire diameter L over T were the most efficient intensity measure to characterize the fire severity, and also the most sufficiently relatively to the other intensity measure that we used. And we could build up these five fragility functions that can be used to assess, to quantify the structural capacity of this steel pipe rack. In the future works, we would use multiple pool fires and also the presence of the wind I would like to thank also a couple of my former PhD students, Jérôme Randax and Luca Possidente, and also the two European projects that were at the base also of these works. So this is the relevant bibliography, so some journal articles that we published on these topics. And then thank you very much for the attention. And then if you have any questions, I will be happy to answer.